Hello all and welcome to the new instalment of the Product Lifecycle series specialising in raw materials. It's brought to you by the Plastics Consultancy Network and the BPF. Before we start, special thanks again to Dr. Robin Kent for putting these all together. Today's webinar is entitled The Hidden Life of PUR and is presented by the lovely Fabrizio Rosato and the great Petra Mikova, both co-owners of Alia. Fabrizio is a polyurethane consultant at Alia and has many years' experience of working in the plastics industry. His job roles have ranged from quality control and quality assurance to R&D and marketing. Fabrizio has strong knowledge of technical issues regarding flexible PUR, viscoelastic, integral foam and elastomers. And then we've got Petra, who is the other half of Alia. She has over 20 years experience in the field of polyurethanes, particularly in formulation systems for varied applications such as footwear, furniture and technical items. And before I hand over to the presentation, if you've got any questions, please pop them in the chat box and we'll get to them at the end. So without further ado, over to you guys, Fabrizio and Petra.
Thank you for this webinar. Our aim is to present the fascinating world of thermoset polyurethanes. Therefore, in order to do it, we will speak about the thermoset and thermoplastic material. So we will see the difference between one and the other. We go on the thermoset polyurethanes. We will have a short story of polyurethanes, the basic chemistry, and the physical structure. So we will look to two main features, that is the density and the hardness. Then we will have a look on the application where you can find the polyurethanes, thermoset, an introduction to the machines to produce the polyurethane, and then have a look also on the recycling and reusing. So let's start with a quick look on the probably best known polymers, the thermoplastic. As probably most of you know, those type of plastic are generally presented to the market as a solid form, so powders or granules. Those solid parts are melted and melted down, so we need energy. And then they pass again in the solid state, according to the shape we want. This process is possible to repeat several times. We lose some properties maybe, but it's possible to melt it down, the items we produce, to have again solid and again and again. This is a chart showing probably the most known thermoplastic process, the injection molding. We see for sure the granules, injection molding press, and operating scheme. Let's go deeply more in the thermoplastic, in the thermoset polyurethane chemistry. The thermoset polymers are completely different than thermoplastic. In this case, we start from liquids, at least two liquids. We put them together and we can obtain energy, even higher than 130 degrees, and our solid polymer. In our special case of polyurethanes, we start from two basic liquids, polyol and isocyanate. We get energy and we can obtain our solid. This process is different from the thermoplastics because one produced cannot be, those items cannot be melted again. It's possible to, as a special chemical reaction, for example, the glycolysis, but it's an irreversible process. As we said, we are starting from liquids. So to transport and store the raw material, we need a container for liquids like bulk, like IBC, drums, tubes, and so on. On the right side, a small scheme on a standalone pouring machine. And in the bottom, we can have a small typical aluminum mold.
Okay, now let's talk about two fundamental components for the production of polyurethane. It's polyol and isocyanate. Commonly, they are called A and B. Polyol, in fact, is not only one component, but we call it also polyol system, and it's just a mixture of additives like crosslinker, catalase, blow-in aging, and so on, and base polyols. The major characteristic or very important characteristic of polyol system is the presence of reactive OH groups. These OH groups then can react with reactive groups of isocyanates. Isocyanates are usually mixture of various isomers of MDIs or TDIs. Sometimes we use also prepolymers that are just MDI or TDI partially reacted with polyols. And their reactive groups are called NCO group. The reaction between OH group of polyol system and NCO group of isocyanates rise to a chemical bond called polyurethane bond. So this is the basic chemistry of polyurethane. Some word about history. Polyurethane was discovered in 1937 by Otto Bayer at the Bayer laboratories of Leverkusen. Otto Bayer was a German chemist, and his surname has nothing to do with the Bayer company. It's just a chance. He accidentally discovered polyurethane just mixing two substances. Initially, it was a kind of rigid foam for insulation, and it took years and years of development and research to customize the product and starting using polyurethane in various applications. Industrial production began in the 1940s, but due to the Second World War and consequent shortage of raw materials, the market only developed slowly. In 1948, for example, the first application of rigid foam was used as the insulation of barrel of beer, typical for Germans. In 1952, Hennecke developed its first slabstock machine and started the industrial production of TDI, MDI, and polyols. At the beginning of 70s, the world consumption of polyurethane was more or less 1 million tons. At the end of 70s, more than 3 million tons. Up to the year 2002, the world consumption grown about 9 million tons, and it's still growing up to estimated 20 million tons in 2020. On the following chart, you can see the world consumption from 2012 to 2020. We can see that it's still growing, and we can see how it's divided in different final application. So the biggest consumption we can see in flexible foam in red and a rigid foam in blue. These are the most basic, the biggest application. Now I'd like to show you how reaction between polyols and isocyanates happens. So how polyurethane bond is born. It's just a very small. Just have a look. Okay, yeah. This is an example of lab foaming, of lab mixing. You can see it's from YouTube. You can find it on YouTube. So we put just a polyol. We add isocyanate. The quantity of iso we add at this moment is calculated, and the quantity depends on the quantity of reactive groups of the polyol system and isocyanate. Then we stir them well. In this moment, we put the energy also to the system, and the reaction starts. Usually during the laboratory evaluation, we can observe different reaction times. For now, for example, we will see the foam, which is starting to rise. So this is start time or cream time. In this case, the foam is it's a foam. It's foaming, and this is possible because on the polyol side there is a blow-in agent. Without blow-in agent on polyol side, we will obtain polyurethane, but it will be a compact material. So the density will be 1000 kg per cubic meter and so on. the foam is raising. In lab, we can observe gel time or fiber time. It's a time when we can see really the creation of polyurethane bond. And when it stops, it's a rise time. Just a small example. Okay, now let's go deeply to the polyol system. The reaction between polyol and isocyanate cannot happen and cannot be controlled without special help. And for this reason, in the polyol system, we can find a different kind of components, a lot of components, and each of them is responsible for specific property. The very fundamental part are base polyols. Base polyols, we can imagine them as chains, long, less or more long chains, which can be branches or without branches, so linear, but they have functional OH groups, and these groups can react with isocyanates. Selection of these base polyols depends on the final property of a final foam. So, for example, if we select a long chain polyols, we obtain a flexible polyurethane. On the other hand, with short chains and branched polyols, we obtain a rigid foam. Other components, very fundamental for the starting reaction, are catalysts. Catalysts can influence the speed of the reaction and consequently also the molding time. Let's say that without their presence, the reaction doesn't start. More commonly are used amines as a catalyst or also metal-based catalyst, bismuth, tin, or so on. Then we have hardeners or cross-linkers. These are usually small molecules that create bridges between the chains of polyol, and in this way influence the hardness and or stiffness of the polyurethane. Then we have a stabilizer or surfactants. Usually they are special silicones and also non-silicon based, and they influence the structure of the foam by modifying the closing or opening effect of the cells and modifying also distribution and size of the cells. Then we have a blowing agent. They are necessary for the foaming of the polyurethane. And as we see before, without their aid, we will obtain compact material. So they have an influence on the final density of the foam. Generally, we used two types of blowing agent. Physical blowing agent that popularly are called freons, and their usage is typical for the production of items with a thick skin, for integral skin foam. On the other hand, we have a chemical blowing agent. It's just a simply water which reacts during the reaction with isocyanates, producing CO2, and CO2 is used for blowing the foam. And then we have other additives like antistatic, color paints, flame retardant, anti-foaming agents, others and others and others. So there is really a big possibility of the formulation. Let's go to the isocyanates. All organic, every organic compound that contains isocyanate group is called isocyanate, and in the production of polyurethane are very important and the most used diisocyanates. It means isocyanates with two reactive NCO groups. The most known are MDR, methylene diphenyl isocyanate, and TDI, toluene diisocyanate. Both are produced from oil by phosgenation process, starting then from benzene. We have various types, different types of MDIs and TDIs, and different isomers or modified isomers. Very often, to optimize the characteristic of iso side of polyurethane, we produce prepolymers. Prepolymers are just partially reactive isocyanates, so base isocyanates or MDIs or TDIs with base polyols in the presence of different additives like plasticizer, stabilizer, and so on. Production of prepolymers is reaction. It's a chemical reaction, is exothermic, and this reaction must be controlled by heating and cooling. So this industrial process, this is controlled.
Okay, as Petra explained, there are more or less infinite possibilities to create our polymer. It's possible to create material with completely different characteristics by playing appropriately with the proper ingredients. We'd love to compare our polyurethane world with the world of kitchen, or better, with the bakery. For example, with the proper ingredients, we can obtain PUR elastomer, PUR compact materials, like in a bakery, the biscuits or the barred chocolate. Or we can have some flexible polyurethanes that are soft, expanded material, like in the bakery, the carrot cake or the Victoria sponge. Or even we can have some rigid polyurethane foam, so the hard, expanded material, like in the case of meringue or the Torrone sweet. Let's talk a little bit about some two main features, so the density and later on the hardness. For the density, as Petra said, a standard polyurethane compact material is around 1000 kg for cubic meter. For sure, we can add a lot of sealers inside. We can increase the density up to 2000 kilograms per cubic meter. On the opposite side, using proper blowing agent, we can obtain density even lower than 10 kilograms per cubic meter. Here are some filler, typical filler that we can use on our polyurethanes. We have some, for example, calcium carbonate, mainly used for cost reason. We have the barite that is used for sound absorption properties. Or we have several different flame retardant, like the melamine, extended graphite, aluminum phosphate, polyphosphate, or aluminum hydroxide. It's depending on the norms that we have to fulfill. Then we spoke about the hardness. As we've seen, we can have soft and hard polyurethanes. But what means soft and hard? This is a small chart in order to explain what means what means soft and hard. We are in the lower part of the short double zero, even sometimes triple zero, short triple zero. But we can go up to the higher level of short D. For the people that don't know what is those short measurement, they are very simple devices. Is how they looks like. In fact there is a needle with different shape, where there is placed a spring with different resistance to compression.
Okay, so as you can imagine, there are really infinity of combinations of formulating polyurethane and obtaining completely different items. Let's say that basically we can divide them in the groups, and for each group we have a very similar formulation that is used. So we can speak about the flexible foam. This is typical, for example, for furniture, for automotive foam, very soft, high resilience. Then we have a memory foam, low recovery, typical for bedding industry. Integral skin foam, it's a foam formulated with physical blowing agent, so the foam with the skin. Rigid foam, typical for insulation or for buildings. Structural rigid foam is still rigid foam, but with very high mechanical properties. And we have a compact materials, so rigid materials, stiff materials, without usage of blowing agent. Then we have elastomers. They are still compact materials, but very, very excellent mechanical properties. And then we have gel, compact materials, which are extremely soft. On this chart, you can see just in percentage the distribution of different groups of polyurethane, different application. As you can see, the biggest part takes a furniture, more or less 33%, and the commonly used polyurethane in the furniture is a flexible foam. Then we have some up to application, buildings and refrigeration. which used a rigid foam, so with 16 plus 6%, totally 24% for rigid foam. Then we have 20% for automotive, 4% for footwear. Now we would like to describe more in details and show you also some examples, just to have just to can imagine how it works, of following fields: insulation, furniture, automotive, and footwear.
Okay, let's start with the oldest polyurethane, the foams for insulation. We can divide them in two big families, the building one side and the other insulation application on the other side. Let's say that those rigid foams, which have the plastic deformation, not elastic, is the low density. Usually they are lower than 60 kilogram cubic meter, and they have closed cell inside in order to guarantee a good thermal insulation. So we can example like the metal panels, very useful the construction of buildings, or the piping insulation is very useful for piping in order to be able to pump liquids over 100 or 1,000 kilometers. We have a spray insulation, is a rigid foam that is sprayed directly on the items, like in this case on the roof, or injected directly into the walls in order to have insulation on the walls. But we can have also insulation in other applications like the fridge, the refrigeration, or the boilers, or even we have the air piping insulation. Everybody know this very famous 7-star hotels in Dubai, the Burj Al Arab. Probably not all of you is aware that in this building we have more than 7,000 square meter of polyurethane laminated boards for insulation properties. Let's go now for the furniture, another sector where the polyurethane is widely used. We can have components like the sofa lining or the armchair lining, the most known, but we have also rigid foam, structural foam like in this table, or integral skin foam like in this chair. We can have also, as Petra said, pillows, very famous in the viscoelastic, slower recovery foam, or the mattresses, usually combination of viscoelastic, HR foam, and so on. We have also the possibility to use our polyurethane structural foam for lamps. For example, in this case, we have a special material that are suitable for electrical components, so they are UL94 V0 certificate. Or, for example, this chair designed in the late 50s by Werner Panton, and the name is Panton chair, is still used. So it's produced with a structural foam density 600, and up to now there are still remained into the market few of the initial the first production of this chair, and still used. So you can have a look, you can have an overview how long polyurethane can last. Automotive. The automotive polyurethane is really important. 80%, roughly 80% of the total plastics used in automotive is polyurethane. In fact, we have several different types of polyurethane. For example, the seat liner, but we have also the steering wheel or the gear knob. We can have also the dashboard that is made very often is made by several types of polyurethane, elastomers and expanded material. We have several other applications, like for example, cover engine or firewall. But you have also the headliner. We can have also rigid foam like structural foam like the bumpers, and many others. Very interesting is this application, the headbox. Sometimes also even the headbox are made by polyurethane. Sometimes they are using an honeycomb paper structure inside and tissue on the top, and everything is glued together with some special type of polyurethanes.
Okay, footwear is another sector in which polyurethane is present in many applications. Generally, we divide footwear in 3 different groups: fashion, safety, and sport shoes. Polyurethane is present, for example, in safety shoes. In this case, polyurethane is used for the production of outsole and midsole, or sometimes only for midsole, and then this midsole is glued together with different with outsoles produced with different materials like thermoplastic polyurethane or rubber. Then we have the fashion shoe soles. These are monodensity soles. Then we have polyurethane gel, which is used for heel cups. We have insoles. In case of insoles for the shoes, we use or flexible foam or sometimes also memory foam, slow recovery foam. Then we have a trekking shoes. Polyurethane is used for the production of midsole and also outsole. We can produce boots, complete boots. Polyurethane is used for the production of ski boots, for inner part of ski boots, like insole, which is usually very rigid, or tongue. And at least fashion shoe soles, like platforms.
Okay. As Petros, polyurethane, as we can see, is very present in everyday life. Let's have a look on some particular examples. Polyurethane is also used for the wind blade. Sometimes they are made in epoxy resin or something like that. But as to increase the structure of this blade, consider that offshore wind blade can be more than 100 meters every single blade. Sometimes they put inside some structural low density rigid polyurethane in order to increase the stiffness and the hardness. We have also a possibility to use polyurethane for the soil consolidation, so injection directly over under the building in order to save from movement of the terrain. We have also packaging foams. Sometimes those bags are white or gray bags where there is 2 liquid inside. You just need to squeeze those liquid together, shake them, and your bag is started to rise around and wrapping your object. We have some flexible foam, like for example, this foam ball from Doimos, from Decathlon. Or we have electrical encapsulation. We can use polyurethane to encapsulate our electrical parts in order to avoid dust, humidity, or even to avoid that somebody will tamper the electrical component. We have cable crossing. This is made only with the 2 types of different polyurethanes. You can see sometimes during the working on the street during some concert. We have technical wheels, very used in industrial application. You can find polyurethane even a cork stopper. Sometimes, if you take a look on the cork stopper, sometimes they are made by cork powder that is glued together with special polyurethane products. As we see, we have several different applications. That means to produce all those kind of items, we need total different machines. We have a few examples. We have an online distributor for a metal panel production. Here we have a discontinuous production and a slab stock production. This is very useful to produce viscoelastic foam, flexible foam, or sometimes even rigid foam. We have a reaction injection molding process here, a special polyurethane with a fast reaction that is quite similar to the thermoplastic. Then we have a spray machine for the spray foam, like the foam we saw in the roof. We have a footwear injection rotary plant. This is very important for midsole production. And we have probably the most easy and most known, the high pressure foaming machine and low pressure pouring machine. Very similar, but the difference is mainly on the mixing head. Okay, Petra.
Okay, so we can produce a lot of items, as you can see, and after producing this item, we have to think about how to recycle, how to reuse, because actually it's also important to talk about eco-compatibility and about recycling and reusing. Of course, polyurethane thermosets are completely different from thermoplastic. They cannot be just grinded and melted again and again. So we have to think about different ways of recovery technologies. Basically, we can see 4 different technologies of recycling. We can see agglomeration and pulverization. These are mechanical recycling. Then glycolysis, it's a chemical recycling, and energetic recovery. Agglomeration is one of the most interesting processes of the recycling of polyurethane, and it consists in recomposing together of particles of polyurethane by the action of pressure and using a binder to glue them together. Usually also in this case the binder is a kind of polyurethane, it's just modified isocyanate. The particles are usually obtained from the processing of scraps of flexible blocks. The finished product can be processed in a similar way to the conventional polyurethane block, so it can be cut, shaped, glued, and so on. And its quality depends on numerous factors like characteristics of the foam scraps used, on the final density of reagglomerate, on the average size and uniformity of the particles, and also on the type of binder and the quantity of binder we use for them. The foam, agglomerated foam produced in this way has very good absorption capacity, energy absorption capacity. So it can be used for example, gymnastic mats, headdresses, undercarpets, and so on. It's estimated that volumes which are processed in Europe are more or less 20,000 tons per year. Another mechanical way of recovery is pulverization. In this case, we have a process when the scraps of polyurethane are reduced into very, very small particles with the diameter of the order a few tenths of millimeter, which can be obtained by using suitable mills or other technologies. And then these particles are sieved and then premixed to the polyol, which is then reacted with the isocyanates. And we have a chemical recycling and glycolysis. Glycolysis is a process where we try to obtain, to regenerate the starting molecules. So it means that this process consists in treating the forms with glycols or different type of suitable catalyst, which then combined at high temperature and pressure leads to the formation of polyol or series of side products. The polyol that we can obtain by the glycolysis can be then mixed with the new polyol in different percentage, and this depends on its characteristic. In the best case, the percentage can reach up to 90%. This technology is used especially in the footwear industry, in automotive industry, or insulation. So we have seen how polyurethane can be reused by reagglomeration, by pulverization, and glycolysis. By another valid alternative is just energy recovery. So we can add polyurethane to the urban waste during the incineration process. And in this case, the addition of polyurethane doesn't worsen the operation condition of the oven or the composition of the fumes. And polyurethane can be added up to 30% by volume of the waste. Alternatively, the polyurethane scraps can be used alone or mixed together with other plastics in thermoelectric power plants as a partial replacement of traditional fuels such as coal. So this is the last chart. That's all.
This is conclude our presentation. So
if you have some question.
Yes, that is awesome. Thank you so much, guys, for that presentation. It's very insightful. And as ever, as with all of our webinars, what we will be doing is sharing this video along with the slides if you guys would allow it. We have had a couple of questions come in, and the first of which is, can you discuss base polyols and isocyanates? I don't know if I've said that right.
Okay. So maybe you want to know something more about base polyols and isocyanates, because
Yes,
it was
that's the
really
one.
okay. So yeah, polyols are generally based, are polyether based or polyester based. Both are produced
Okay.
from oil by different processes. And for example, the polyester based polyols are historically the first that were used. Then also usage of polyether started. Polyesters are produced by esterification process from acids like adipic acids and so on, with glycols like monoethylene glycol, diethylene glycol, butanediol, and so on. And polyether, on the other hand, are produced by a reaction of starter, which can be a glycol, sucrose, and so on, which ethylene oxide or propylene oxide. This is a reaction of polyaddition. And in this case, we generate chains with different functionality, and the functionality then depends on the starter we used, and different length and different properties. It depends on usage of ethylene oxide or propylene oxide, on the sequences, and so on.
Okay.
Okay.
No. Yeah, that's awesome. And then we've got another question that's come through. What's the difference between a high and a low pressure machine?
Okay, high and low pressure machines, they look like quite similar, especially the standalone machines. The main difference is in the core, so in the mixing head. Let's say that low pressure machines, we speak about machines that in the mixing head there are the two liquids that stay as liquids as they started. They are mixed together with a sort of stirrer. So it's the easiest way to mix our polyol and isocyanates. On the opposite side, at high pressure, those liquids are pumped in a nozzle reaching pressure more than 100 degrees, usually 150 bar, sorry, 100, more than 100 bar, 150 or so on. When we pump those material at those high pressure, the liquids became vapor, and so they are sprayed together, and so the mixing between the two liquids that now are spray is due to the energy that we put inside them. What is the main difference? The main difference is that in the low pressure machines, after the shot, we still have some remaining material partially mixed on the stirrer or in the mixing chamber. So we need to flush it and to clean with proper solvent. Whereas in the high pressure machines, we don't have a stirrer, but the mixing chamber is quite clean, we can easily clean. This is the main difference.
Okay, cool. Yeah, that explains it. We've also had another couple of questions come in just now. I'll start with the first. Could polyurethane be used in master batches and extruded in conventional twin screw extruders?
Probably they are speaking about thermoplastic polyurethanes. Thermoplastic, sure, is a thermoplastic polyurethanes, but it's not thermoset in the extruder. So we start from already produced polyurethanes. It's not a thermoset, I mean.
Okay. And then the last one that we have so far is, can we add plasticizer in polyolefin system instead of an isocyanate system? If so, is there a difference in performance at the end?
Yeah, sure. We can add plasticizers on both sides, on polyol side and also iso side. Very often, this choice is driven by a desired viscosity we can obtain. So that's sometimes this choice is like this, to use it on the polyol, on the iso. Generally, there is no difference in the final properties of the polyurethane because plasticizer doesn't react in the reaction, so the final properties is the same.
It's very important, of course, to know exactly the application, the mixing ratio that we are speaking about, the type of the machines, because to choose if to use a plasticizer on both sides or only to one or on the other side.
Okay, awesome. That's good. And I think that's all the questions we have. So I think we've come to the end of the webinar. I just wanted to say a huge thanks again to you guys for coming and doing these presentations. It's been awesome. We will, as I said, put this video along with the slides up on the website for you guys to kind of like have a copy of that are listening. And also, yeah, I think that's it. Now there will be a feedback form for everyone that's listening that will be going out, and that's going to go out today just to kind of see exactly how this webinar has gone. I'm sure it's been brilliant. It's been really well put together. Actually, before we go, we've just had a last question, and this is the last question, okay? Because I think people now are knowing that it's coming to the end, and I think that's when they're sending their questions through, which is great. It's which type of plasticizers are generally used?
Like TCPP, Benzoflex, and so on.
There are several types.
There are several types of plasticizer. I think that plasticizers used in polyurethane are very similar to plasticizers used also in thermoplastic.
Could be used also.
Very similar.
Okay, and what one would be best one?
You want the market because some plasticizers are not more allowed in Europe, maybe yes in the Asia or so.
Ah, that makes sense. Okay, cool. All right then. So I think that, yeah, that definitely answers everything. So yeah, so any final words, guys, before I finish the webinar?
No, I think no.
Okay, cool. Awesome. So that's it now. So thank you again, and we look forward to working with you guys again soon. So have a great rest of the day, and we'll speak to you soon.
Thank you.
Thank you very much.
Thank you for everybody.